Hi, my name is Steve Ward, and I'm going to give you a brief overview of digital communications. Digital communications is sending data using digital methods, typically based on computer technology. This occurs at multiple levels. Inside computers, we send data on internal communication buses. Between the computer and peripherals, for example, we send data between keyboards, mice, printers and screens and the computer itself. We also send data between computers, for example, from a client to a server. And we send data between computers and the internet, which is really just another example of client-to-server communications, but now we have a much wider network, including the World Wide Web and the internet. An increasing number of devices are now computer-based, from watches and phones, laptops, desktop computers, and of course, as mentioned, servers and the internet itself. We'll start with bits. The smallest amount of data that can be sent is a bit. A bit represents either a 0 or 1, and at the physical layer, this can be represented by the presence or absence of light, or the presence or absence of current or voltage, or by a radio frequency. The signal is maintained for an amount of time before the next bit is transmitted. The physical layer needs additional bits to be sent to synchronize timing between the sender and the receiver, and the physical layer may also use additional bits in an encoding system to make sure that the signal changes regularly, as otherwise capacitance on the wire or some sorts of communication propagation mechanisms, they can't cope with a constant communication. And also, changing the bits also helps include timing signals into the actual message, which can again help the receiving device understand what message is being sent. Bits are commonly combined into groups of 8 to make a byte. This is partly for historical reasons, because early computer systems used 8 bits to represent a byte, and with a byte, they can be combined to represent a character. For example, there's the American Standard Code for Information Interchange, or ASCII. That can use 7 bits for up to 127 characters. And more recently, we have Unicode, which can use 8 or more bits to represent many more characters. And that's required for multiple languages and emojis and so on. Multiple characters can represent a string of text, and this can be used by humans to read a text message or a document or some other sort of message in a humanable readable format. But the bytes themselves can also be used by the computer themselves in binary format. Bits can be combined to represent numbers. So for example, 8 bits could represent a number between 0 and 255, or using a signed bit, we could use that to represent a number between minus 128 or up to plus 127. 8 bits is very useful, so often we use word or integer maths where we use 2 groups of 8 bits or 2 groups of 2 bytes or 16 bits, and in this case now we can represent numbers between 0 to 65,535, or again by assigning a sign bit we can go from minus 32,768 up to plus 32,767. Again, 16 bits may not be too useful, so often we use 32 bits to represent either larger integer numbers or floating point numbers. And there are other number formats as well, using even more bits. The more bits you have, the bigger or smaller the number, and also the more resolution it can have in the terms of the number of actual digits that can be expressed. And with modern systems, bits can be combined to represent images and other documents. So for example, we can have basic bitmaps where the bits represent a simple image, but then there are various compression formats like GIF and JPEG, and then we can also have larger documents like PDF, and of course typical files like Microsoft Word, Excel, PowerPoint, AutoCAD files, and so on. Now, to actually send the data over a network, most modern networks use a serial interface where we send one bit at a time, one after another. The alternative to a serial network would be a parallel network, and these were used in the early days of computers, and are still used inside some computer networks as the data bus. But outside of the computer and between peripherals, most modern networks today are serial. The idea is the receiving device receives the bits, and then it converts those bits into the required format and then handles the response. Usually you need one communication channel in each direction. So typically with a cable system that would need 2 or more cables. There are some fiber networks which allow bidirectional communication on a single fiber, but normally you need some sort of protocol or handshaking to manage which is sending and which is receiving, and that requires that you have multiple communication channels. There are many serial networks including Ethernet, RS-232, RS-485, 422, Universal Serial Bus, and lots of internal computer buses, as well as lots of proprietary networks. Sending data via a serial link is generally easy. If you just want to send a bit, you just modulate the carrier to on or off. So that could be turning the voltage on or turning the voltage off, or supplying current or voltage. Or if you're modulating a carrier network, you may change frequencies, or you may just change the amplitude of a single frequency. To send a byte, you need to do a bit more work. First of all, you need to synchronize the sender and receiver, typically with some sort of preamble, and then followed by some sort of encoding in the message. So the preamble tells the receiving device to get ready to receive data, and then the encoding is intended to actually tell the receiver that we are sending data. And again, it's required to avoid sending too many bits of the same value, one after another. That can involve overcoming issues with capacitance on the line, which would mean that, for example, a voltage would tend towards 0 after a while. And it can also help with timing on the system as well. Typical encoding systems include Manchester encoding or 8B, 10B encoding. And these actually require more bits than you would normally send to make a byte, but often that's grouped at multiple byte levels. So it does involve a bit more data, but it does allow the sender and the receiver to be properly synchronized to make sure the messages are received correctly. What you also need is additional bits to actually define the start of the message. So you have a start bit, you have a stop bit typically at the end of the message. And because electrical noise could affect the signal, we often have additional bits like a parity bit, which allows for corruption of the data. And then if a single bit is detected as being wrong, that parity bit can be used to detect that. And then we can extend that at the byte and message level with block check characters and cyclic redundancy checks. With things like ECC, error correction, we can even overcome single bit errors as well as actually just detect them. At the message level, we also need to detect non-receipt. Some systems use broadcast messages, but in most applications, we need to send the message and we need to detect if the message was received. So typically that's with some sort of response timeout. And if the message wasn't received, we need to resend. Now, Ethernet is the commonest local network for wired applications. Ethernet is standard under IEEE 802.3, and there are various standards in use. Originally it started off as a 10 megabit system using a shared backbone based on coaxial cable. And because it was a shared backbone, there had to be a lot of electronics and handshaking involved, because if multiple devices tried to send data at the same time, the message would be corrupted and then not received correctly. So there was a carrier sensing, and then the idea was that devices would detect if there was any collision, and if so, back off. Modern networks tend to be a lot faster, typically 100 megabits or more likely 1 gigabit. And what we now use is a Cat5 cable, which involves multiple unshielded twisted pairs, and then we have RJ45 connectors that plug into switches. The switches handle the backbone, and they can also handle multiple devices, including multiple devices talking to each other at the same time. So we get faster speed, and then with the backbone and multiple device handling, we also get greater throughput because multiple devices can be communicating simultaneously. And even in the Cat5 cable itself, there are multiple pairs. Typically there are 2 pairs for sending data and 2 pairs for receiving data, and that increases the bandwidth as well. Now there is a restriction. If you're using the standard Cat5e unshielded twisted pair or UTP cable, the maximum distance is 100 meters, but we can link switches or we can use fibre cables or other technology to achieve longer distances. What you'll typically find in a large application, like a building or a factory, is a structured cabling system where there are 100-metre runs from your desk or from your device into a structured cable cabinet, and then there is sort of some even higher speed backbone running between those structured cable units between floors or across campuses or across whatever your structure of your building needs to be. And those backbones, they're often running at much faster than 1 gigabit, up to 40 gigabits or more, and possibly using parallel connections as well for higher data throughput. Now, increasingly, we don't actually connect devices via wires anymore. We use wireless networks. This is very common for peripherals such as keyboards and mouse using Bluetooth, and also for Wi-Fi, but also for a lot of electronic devices, your phones, TVs, even fridges. You will connect via Wi-Fi. So Wi-Fi is standardized under IEEE 802.11, and the idea of these networks is, combined with wired networks, then they can send lots of data using the electromagnetic radiation for sending data rather than using a physical wire. So typically these are wireless, using radio waves. Electromagnetic radiation used to include infrared, but that's very rarely used these days. It's normally radio frequency data that's being sent. Wireless networks today are very complex. They started simply with amplitude modulation for transmitting serial data, but today we often use multiple high frequencies with frequency modulation, and there are lots of techniques for sending data using multiple in, multiple out, and also to allow multiple devices to share different or slightly different radio waves, but in the same sort of band, and to allow multiple devices to communicate together. Additionally, with the frequencies we're using, typically that would be 2.4 gigahertz, but these days we can also use 5 or even 6 gigahertz. The higher the frequency, the lower the distance, but the more data we can send. And by combining multiple frequencies, we can now have almost as much throughput with a wireless network as we would with a wired network. Now, getting bits from one end to the other is part of what we need to do, but that doesn't really give us much information about what the actual bits mean. If it's a dedicated communication network, then the device manufacturer can probably just sort that out and decide what the bits mean, but most systems use products from more than one manufacturer. So what we use is a protocol which defines what the bits mean, and it allows interoperation of the devices from different vendors. Now, there are many protocols such as TCP/IP that we use for accessing the internet, along with HTTP or HTTPS for actually handling things like web pages, FTP for file transfer, and so on. And the idea of these protocols, they define various aspects, including handshaking and link establishment and shutdown. A bit like when you make a phone call, you have to dial someone up, they have to answer, and then you'll have a brief conversation to establish who you are before you get down to the nature of the actual conversation itself. And then there may be, goodbye or see you soon, and then of course you'll close that connection. Protocols do a similar sort of thing, but at a lower, more electronic level. There may be various request and response formats. So for example, if you need some data from another device, you'll perform the handshaking, and then you'll send a request message, and then the other device will process that and send a response message containing the data that you've asked for. Then, of course, we need to establish what the data is. So there are data formats, as we've seen before, to handle things like strings or text, numbers, files, and so on. And another aspect we need to handle is data that's too long or too big for a single packet or frame on the network. The idea is there that typically we only send a few hundred or maybe a few thousand bytes at a time, and that's not enough to handle modern files or images or streaming a video or so on. So what we need to do is we need to handle how those large amounts of data are sent across multiple packets that are actually sent on the low-level network itself. Common protocols we come across. Modbus is one for industrial applications. Modbus RTU is a serial interface using the RS-232 or 422 or 485 physical layer, allowing one or up to a few devices to be connected over a simple local network. These days that's replaced by Modbus TCP, which is Ethernet based. And Modbus, it's a sort of standard or de facto standard protocol that's adopted by many different devices. It's not completely standardized, but it's close enough that normally two Modbus devices would be able to talk to each other, and it's also quite easy to convert from Modbus RTU on serial to Ethernet and vice versa. So this allows a lot of interoperability between current and legacy industrial devices. Another protocol is Ethernet. At the physical layer, there are two layers which actually perform the sending and receiving of bits and the transfer of sending and receiving those bits into bytes. So the IEEE 802.3 physical layer is itself a protocol, as well as being a hardware standard for the actual wires themselves. TCP/IP I mentioned earlier, that's a protocol that's used to send data over the internet. HTTP and FTP, I mentioned those as well, used for sending web pages and files. And then beyond that, we do get specific protocols to handle other sorts of data. So for example, an industrial Internet of Things protocols include OPC-UA for sending data with lots of context, and MQTT, which sends simpler messages, which include typically an identifier and the actual data packet itself. And often with the MQTT protocol in particular, you then need to add some additional context on top of the data. So there's a variety of different layers here at which the data can be sent, ranging from the bit or byte layer all the way up to an actual defined message that can be read and understood and interpreted by the machine or even by the people who need that data. Now, as file sizes get larger and as the amount of data increases, people are often concerned with the maximum speed, and that's limited by physical aspects of the link. In cable systems using copper, or in the past even aluminium cable, capacitance and inductance limits, they would limit the rise and fall time, which affected the overall speed across those older cables. And in metal cables, electrical resistance can also be an issue as well. If the cable is long enough, the signal will be attenuated and it will no longer be able to be read by the device at the other end. And also, as the voltage drops, the cable itself can be more and more affected by noise, which can override the actual signal. Optical systems have longer distances, but they can have limits of opacity in the cable, and that again can limit how far you can send a piece of light across that cable and how far that cable can be. With both of these, there are mechanisms of having repeaters which can receive data and boost it. But if you've got a very long cable, you could end up needing a lot of repeaters, each of which needs power, and that can cause problems in the physical implementation of these systems. If we're sending radio waves, then radio waves are absorbed in the atmosphere. Normally, if it was just normal air, then the distance can be quite far. But if there's any sort of moisture in the air, particularly if it gets very foggy or if there are clouds, that can affect how far we can propagate a radio signal. Another aspect of radio signals is, of course, you've got line of sight. For very long networks, the horizon gets in the way, or maybe trees or mountains get in the way. So you need some other mechanisms there to send that data via radio waves, possibly bouncing off of the ionosphere, although that's limited at certain times of day. Or again, you may need repeater stations. There are, of course, electronic switching limits, but the amount of time you can send a bit is limited by the switching time of a transistor. Generally, that's not one of the issues in modern networks. It's normally one of these previous limits on the actual physical media, but on very short but very fast networks, electronic switching time does become an issue. Transistor sizes are shrinking, and as transistor sizes shrink, there's less resistance and capacitance in the system, which is allowing faster switching times. But the technology is taking time to get there, and at the moment, the electronic switching time is the ultimate limit for us. You also have some systems where if you're using the same carrier for both sending and receiving, you do have to switch from transmit to receive, and that can cause timing issues. So typically, if you're using some sort of radio mechanism or a single wire, maybe on a telephone system like we used to, you would have like a modem turnaround time, and that could be set to say 100 milliseconds. So that would be quite a substantial time to allow the switching devices to transmit and then switch to receive, and that of course would limit your overall speed of processing time. Processing time is also required to decode the protocol, to calculate checksums, to handle encryption. So again, we're limited by the physical speed of the electronics to actually be able to handle that. As I said, often for longer distances, we make up of multiple segments, but they also add to delays. Each time you have a repeater, each time you have sort of conversion from one media to another, or each time you want to handle checksums and encryption locally, all of that adds its own delays, and all of those have limitations as well. Having said that, modern networks are very fast. We can achieve easily 1 gigabit over a physical cable using Ethernet. We can achieve several hundred megabits using Wi-Fi, depending on the distance. Again, the longer the distance with Wi-Fi, generally the slower the speed, and vice versa. Fiber optic networks can be extremely fast, and we can bundle multiple fibers and even use them in parallel to get faster speeds. So with those backbone links, speed isn't generally the issue, but we do run up against limitations of cost. So speed is pretty fast today, but there are still physical limits that we hit that ultimately limit us. Now, if you have a network and you want to calculate throughput, you can do that. Simplest way is to add up the amount of data that will be sent, then add a protocol overhead. The protocol overhead is those extra bits which are required for error detection and correction, the start and stop bits and so on. But also there's additional protocol overhead for the sending and receiving, maybe for the encryption, maybe for anything else depending on the protocol. And it depends on the protocol as to what that overhead will be. But for longer messages, it's typically 10 to 20%. But if you're only sending very small amounts of data, the protocol overhead could be significantly higher than this. For example, if you're doing Modbus RTU, a simple serial read request, there are 13 bytes of overhead in the request, and then you get the result. But so that's 13 bytes plus whatever your actual data payload is. Now, if you're requesting, say, 10 bytes, that would mean you've got a 23 byte message, of which 13 bytes would be the protocol overhead. So that's quite significant. That's more than 50%. But if you're reading, say, 128 bytes, then of course you've got 13 over 128. So now you're only down to 10 bytes or 10% rather for the overhead. So you can calculate this and you can make estimates, and you could also do a worst case. So there are multiple ways of calculating throughput and the sorts of response times you can receive. So let's finish up with a worked example of throughput. This is through an industrial control system with 30,000 I/O tags spread across 52 devices. We have to allow for the differences between discrete data and analog data, with discrete data using 1 bit or 8 bits per byte. But if we've got analogs, then they are sent typically as 16 bits or possibly as a 32-bit reel. But in this case, we'll assume 16 bits for the analogs. So working on a typical split of 40% of DI, 30% of DO, 20% AI and 10% AO, we can calculate the amount of DI, AI per device. So we can work out 30,000 overall, divided by 52 for the number of devices, multiply by the percentage, and then from that we can calculate there the overall number of bytes, and we can say that that will be one read request of 43 bytes of data for the discrete inputs. For the analogs, we've got a slightly different calculation because there are fewer analogs, but each one takes more data. So now we've got 232 bytes, or effectively a read request of 245 bytes. So that's the amount of data we have. In this system, if it's HMI SCADA, typically you're reading the DI and the AI on a regular basis, but the DO and AO are normally set points, and they're acyclic when the operator performs a set point. So for that one, you can just assume a single set point per second, which would probably be more than you'd get in practice. So that gives us a total per device of 303 bytes, and then you can multiply that up by all devices, which gives us 157,560 bits. So if we had a 512 kilobit maximum bandwidth network, such as we would have with a radio system, divide that by 157, and then we can get 3.24 updates per second maximum.